let's recall where we were from last video. So last video we want to show that this map that maps a LQ function to the dual space of LP that's going to be surjective. In other words, we pick any linear function of phi from the dual space in LP, and then let's with the assumption that the x is the mu of x, or mu is a finite measure. Basically, we constructed a function g where we showed this phi of f when you evaluate a simple function is in this form of an integral of f and g d mu. Okay, so essentially we want to show this phi is in the form of some phi, big phi of g, where g is in LQ. So last time at the end, we say that basically we need two technical details. So first of all, I need to show this G is in the LQ. And second, I need to show that not only phi of f for simple function, it has this form of the integral of g, but it is also for all the LP function. Okay, so this phi is indeed equals to the big phi of g. Okay, that's our goal. Basically, that shows the surjectivity of that big phi. All right, so the first thing we want to prove is this g is an LQ function. The idea is fairly simple. So if you recall what we did, if you have some function g inside LQ, we used this function f, where f is the g to the raised to the q minus 1 times the psi of g divided by g, the q norm raised to the q minus 1. That's how I proved the phi g, the operator norm of phi g is equal to the q norm of g, okay? But there are two problems. So first of all, here we don't know g is inside LQ, so we don't know that. And second, this f is now simple. Okay, so right now we only know how to evaluate phi of a simple function. So here really the simple function is the key. So we can't do the same trick, but we can use something similar. Okay, so here is what we're going to prove. All right, so to show g is inside LQ, well, I just basically need to show the absolute value of g is inside LQ. So the absolute value of g is greater than or equal to 0. G is the Radon-Nikodym derivative, so g is measurable, so this is clearly measurable. The absolute value is also measurable, so I can pick some increasing sequence of simple functions that converge to these absolute value of g from below. Okay, so there exist some, let's call them psi of n. Okay, so they are simple functions, and they have these psi of n, they're increasing, and the pointwise limit of these psi of x is equals to the absolute value of g of x. Okay, so that we know. Okay, because we also have this assumption that mu of x is less than infinity, so everything, all the characteristic functions are in LQ or in LP. So this phi n, they are in LP, LQ as well. Okay, so basically that allow us to use this trick. Okay, that allow us to use this trick. Okay, so we can apply to this psi of n. Okay, we know they are in LQ. Okay, so let's consider a bunch of functions. Let's call them fn. Okay, so these fn, I cannot use g, so I have used psi. Okay, so let's use psi n raised to the power q minus 1. And then again, I need to multiply the psi of g. Okay, so that when I multiply the g, I got a copy of the absolute value of g. And then when I divide, I cannot use the q norm of g because I don't know g is in LQ yet. So let's write psi n, their q norm raised to the power q minus 1. Okay. So let's observe a few things. So first of all, this psi n, they are in LQ. So we have, using very similar trick, we have these the p norm of these fn. Okay, they are going to be equals to 1. Okay. So it's essentially the same trick. You raise to the power p times q minus 1 is equal to q, and just do the integral. And second, each of these phi n are simple. So the reason is because I have psi n are simple. So raised to the power q minus 1 is also simple. The sign of g is either positive or negative 1. And then now I divide everything by a constant. So this fn is going to be a simple function. Okay, so all of them are simple. And so if I consider the following, so well, first of all, that's one thing we immediately know when they're simple and they're equals to 1. then if I consider the supremum of each of phi of fn, I evaluate fn using this linear function of phi. Well, that's going to be less than equals to the operator norm of phi. Okay, that's going to be less than infinity. Okay, so this we know. And on the other hand, each of these phi of fn, because fn is a simple function, so this is the, let's put the absolute value outside. This is the integral of fn g d mu. And let's just write using the definition. So fn is equals to psi n raised to the power q minus 1, okay? And I divide the constant, which is psi n raised to the q minus 1, the q norm raised to the q minus 1. And then I also multiply a copy of the sine of g times the absolute value of g, okay, d mu. Well, everything here is really positive, so let's just remove the absolute value outside. All right, and one thing you know is because the psi n are increasing to g, okay, so I have, this is certainly greater than equals to the integral of psi n raised to the power q divided by all these psi n raised to the power q minus 1, their q norm raised to the power q minus 1. And this is essentially just the psi n, the q norm of psi n. Okay, so this is the q norm of psi n. So now we see the q norm of each of these psi n is bounded above by the absolute value of phi of fn, which if I go back here, is bounded above by the operator norm of this function of phi, okay? So here, if you recall, these phi n will converge to the absolute value of g in pointwise. So each of these phi n raised to the power q will converge to the g to the power q pointwise. Okay, so if you want to consider the integral of g to the power q d mu, okay, this is the integral of a limit, so you use the Fatou's lemma. That's going to be less than equals to the lim inf, because this is equals to the limit, and the lim inf is going to be less than equals to the supremum, so let's just say it's less than equals to the supremum of, maybe I should write it the other way, let's just write the integral, okay, so this is the integral of the psi n raised to the power q d mu. And each of these integral is just equals to the q norm raised to the power q, but each of these is again bounded above by the operator norm phi raised to the power q, but the whole point is this is less than infinity, okay? So this shows that the integral of absolute value of g raised to the power q has finite integral, so g by definition that's going to be an LQ function, okay? So now we proved g is inside LQ. So the second one, I want to prove that this integral formula can be extended to all the LP function, okay? So let's show that. So for every f inside the LP of mu, okay, let's just consider the case when f is non-negative. Again, because it's an LP, so it's measurable, so there exists some simple function. We already seen these kind of trick multiple times. They're increasing, simple, non-negative, and they converge to this f, okay? And because they have convergence pointwisely, you also have each of these to the raised to the power p is less than or equals to f raised to the power p, okay? And then if you consider the integral of the f minus fn raised to the power p, you consider the p norm difference, so this is f minus fn inside the p norm raised to the power p. Okay, so this one, first of all, you know it pointwise converges to 0, and if you can use some dominated convergence, then let's find the dominated function. While you have f minus fn raised to the power p is bounded above by 2 to the p times the absolute value of f to the power p, because you first use triangle inequality, that's less than or equal to f absolute value plus the fn absolute value, and then you use fn absolute value is less than or equal to f. So there you have this inequality, but this one is an L1 function, so because f raised to the power p is in L1. Okay, so this whole thing is going to converge to pointwise. The limit of the integral is the integral of the limit, so this one will converge to 0. Okay, so in other words, we have the fn will converge to f not just pointwise, but also inside the LP norm. Okay, in LP norm. Okay, because of that, so now if I consider what happens to this phi of f, okay, because I have phi of f is the f is an LP limit of the fn, okay, so this one is also equal to the LP limit, well, the phi limit of the phi of fn, okay, because phi is continuous. So here we use phi is continuous. Okay, so fn converts to f in LP. Phi is in the dual space of LP, so it's a continuous map from LP to R. So this is, I can write this limit. And now because each of these fn is a simple function, so now I can use the what we showed from last video. So this is the integral of fn g d mu. This is because fn is simple. All right, so basically I just need to show that this limit is equals to the integral of fg d mu. Okay, if I can show that, then I'm done. Okay, so to consider this limit, well, it suffices to consider their difference. Okay, so let's consider fg minus fng, their difference d mu. Well, this is less than equals to what? Well, first of all, if I just let's put the absolute value here is less than equals to the integral of the absolute value, and I can factor them as fn minus f, and also multiply the absolute value of g. And when you multiply something, well, this is in LP, and this is in LQ, we just showed g is in LQ. So by Holder's inequality, this is bounded up by the difference of the f minus fn in P norm and multiply by the Q norm of G. And you realize, well, if n goes to infinity, we just showed fn converges to f in LP norm, so the P norm will go to 0. The Q norm of G is a constant, so this goes to 0 as n goes to infinity. Okay, so I have this limit also converge. Okay, so that's essentially proves the desired equality here. Okay, so this proves the last bit of equality. So what I have is phi of f is always equals to the integral of fg d mu for all f here. Okay, well, wait a second, I assume f is only positive. Okay, for all positive f. And for negative f, well, you just use the linearity. You have when f is just an LP function, you take the positive part f plus, and you take the negative part f minus. You do basically the same trick, and f is the phi map is linear, and the integral is linear, so that's fairly simple. So in any case, what we showed is the following: we showed phi of f is equals to the integral of fg d mu. That's for all f inside the LP space. Okay, all f in LP of mu. In other words, this is the same as phi g of f. Okay. So this essentially shows the following. So for every phi inside the LP dual space LP mu, the dual space of LP, then I can always find the G inside the LQ space, so that phi is equals to a big phi of G. In other words, this big phi of G is going to be surjection. Okay, so it's onto map basically. All right, so let's finish basically the whole proof. There's only one little difference is that here I made the assumption that mu is a finite measure. Well, if in general, if it's a sigma finite measure, you do the same procedure restricted to a set of finite measure, and you do the limit. Okay, I'm going to leave that as an exercise. I just want to quickly mention this notion called a reflexive Banach space. So a Banach space V is called reflexive is if its double dual space is isometrically isomorphic to V itself. Okay, so the double dual space is essentially because the dual space itself is a Banach space, I can do the dual space of the dual space. So I got a double dual space. Okay, so that's isometrically isomorphic to V. So not all Banach spaces are going to be reflexive. Okay, so in fact, the L1 space is not reflexive. Okay. But the immediate corollary is that the LP space of some sigma finite measurable space is going to be reflexive. So for every strictly p strictly greater than 1, strictly less than infinity, we basically prove the LP of mu is going to be reflexive. Okay, so the reason is that the LP of mu, the double dual space, is essentially just the, first of all, is the dual space, the whole thing to the dual, and the dual space is the LQ, where P and Q satisfy the Holder's inequality, and LQ dual is also equals to LP. Okay, so you do the other way around, you move back to P. So they're the dual of each other. And another quick corollary is one thing is fairly interesting is when P is equal to 2, then you have 1/2 plus a half is equal to 1. So the L2 space is the dual of itself. Okay, so the dual space of L2 is again just the L2. This is not surprising because the L2 of mu is actually a Hilbert space. It's an inner product space. Okay, so you can, if you go to functional analysis, you probably learned all Hilbert space. The dual space of any Hilbert space is itself. Okay, it's isometrically isomorphic to itself. Hilbert space basically means I have an inner product. Okay, so you have f and g, the inner product is just equals to fg d mu. For here, f and g is inside the L2 of mu. Okay, so that put the inner product structure on this Hilbert space, and it's a complete inner product space. That's what we call the Hilbert space. And the dual space of this L2 space is always itself. Okay, so it's a self-dual.